Good morning everyone. Today, I am going to present a fundamental yet highly crucial topic in engineering mechanics, free body diagrams and equilibrium. Whether we are designing a massive suspension bridge or a tiny machine component, every engineered structure relies entirely on these core principles. In this presentation, we will walk through how to isolate a system, identify the forces acting on it, and apply equilibrium equations to solve real-world engineering problems. Let's start with the core concept. What is equilibrium? Simply put, a body is said to be in equilibrium when the net resultant force acting on it is exactly zero. This is a direct consequence of Newton's first law. We classify equilibrium into two distinct types based on motion. First, we have static equilibrium, where the body is completely at rest, meaning both its velocity and acceleration are zero, which is the most common scenario in structural engineering for objects like bridges and buildings. Second, we have dynamic equilibrium, where the body is actually moving, but with a constant, uniform velocity. Because the velocity does not change, the acceleration is still zero, such as an aircraft in a steady, level flight. In both scenarios, the net external force remains absolutely zero. Before we can analyze any object, we must accurately identify and classify the force systems involved. Forces generally fall into two fundamental categories, active and reactive. Active forces are those that actively tend to move or deform the body. These are applied externally and drive the system, such as applied point loads, distributed loads, or the weight of the body itself acting vertically downward through its center of gravity. On the other hand, reactive forces do not initiate motion, instead, they resist it. These are forces exerted by constraints or supports that exist only in response to active forces, such as the normal reaction from a surface, friction forces, or tension inside a pulled rope. To solve these complex structural problems, we use a powerful tool called a free body diagram, or FBD. An FBD is a simplified diagrammatic representation where we mentally detach or free the body from all its surrounding supports and environment. This process reduces a complex physical structure into a clean, workable mathematical model. Drawing a correct FBD is the single most critical step in engineering mechanics. If your FBD is wrong, the entire calculation that follows will be completely wrong. A complete FBD must explicitly show all active forces, the body's weight, all support reactions, and all known magnitudes, directions, and angles. To ensure no force is missed, we should always follow a disciplined four-step approach when constructing an FBD. First, isolate the body by mentally separating the chosen system from all its surroundings and connected bodies. Second, show active forces by drawing all applied loads and the body's weight acting vertically downward through the center of gravity. Third, replace supports with reactions by removing the physical constraints and substituting them with the exact force or moment they exert. Fourth, label everything clearly, marking known values and assigning variables to unknown forces. Correctly identifying support reactions is the most error-prone step in FBD construction, so we must understand how each support constrains motion. A flexible cable only prevents a body from moving away along its line, so we draw a single tension force acting away from the body. A smooth surface or a roller support allows free movement parallel to the surface but prevents penetration, creating exactly one normal reaction force perpendicular to the surface. A hinged or pinned joint allows the body to rotate freely but prevents translation, requiring two reaction components, one horizontal and one vertical. Finally, a fixed or built-in support prevents all translation and all rotation, which requires drawing three reactions, a horizontal force, a vertical force, and a resisting bending moment. Once the FBD is correctly drawn, we apply the mathematical equations of equilibrium. For a 2D or coplanar force system, where all forces lie in a single plane, three scalar equations govern the system. The sum of horizontal forces must equal 0, the sum of vertical forces must equal 0, and the sum of moments about any arbitrary point O must equal 0 to prevent rotation. With these three equations, we can solve for up to three unknown forces. Next, we have a very useful shortcut known as Lami's theorem. This is a special case theorem that applies only when a particle is in equilibrium under exactly three coplanar, concurrent, and non-collinear forces. It states that if three forces acting at a point are in equilibrium, each force is directly proportional to the sine of the angle between the other two forces. Instead of resolving every force into x and y components, Lami's theorem allows us to find unknown forces much faster using a simple trigonometric ratio. In the real world, engineering structures are three-dimensional space systems. For 3D systems, particles can translate and rotate along three axes, x, y, and z. Therefore, three equations are no longer enough. We require six scalar equations of equilibrium. To prevent translation, the forces along all three axes must balance out to zero. To prevent rotation, the moments about all three axes must also balance out to zero. With these 6 equations, we can solve up to 6 unknown variables. When tackling any mechanics problem, jumping straight into calculations leads to errors. Use this structured 5-step workflow. Read and visualize the system, draw the FBD carefully, choose a coordinate system that aligns with the dominant force directions to simplify calculations, apply the equilibrium equations while picking a moment center that eliminates the maximum number of unknowns, and finally, solve the algebraic equations while verifying your units. To conclude, these concepts are applied daily across all engineering fields. Civil engineers use them to ensure structures withstand gravity and wind loads, mechanical engineers use them to analyze machine mechanisms and gear forces, and aerospace engineers use them to balance lift, drag, thrust, and weight for stable flight. Remember, the FBD always comes first. Equilibrium means forces and moments perfectly balance out, and mastering these basics is essential for advanced subjects like strength of materials. That brings me to the end of my presentation. Thank you so much for your time and attention. I would now be happy to open the floor to any questions you might have.